Thanks for coming to my talk. I'm Jacob, a fifth-year CS PhD student at the University of Illinois, and this is joint work done with Gagandeep, Singh, and my advisor, Sasa Misailovic. So as we all know, we're currently in the midst of a machine learning revolution, where AI is now affecting nearly all aspects of our lives. However, formal verification of these models is highly necessary to ensure their trustworthiness. For instance, imagine a driverless car sees a perturbed image of a stop sign and incorrectly decides to keep going, which sadly has been shown to happen because of the highly complex decision boundaries on these networks. Hence, we need to be able to rigorously quantify and reason about such behavior. To obtain formal guarantees on these networks, significant prior work focused on bounding the Lipschitz concept, which is useful for analyzing the network's decision boundary. However, our contribution is to bound the local Lipschitz concept with respect to the perturbation function, in this case, the amount of rotation. This is something that no prior work could handle, and intuitively, this allows us to quantify how much a perturbed image can differ in its classification output as a function of the perturbation amount. Stated more formally, for a neural network F, a perturbation function P, like rotation, a set of parameters X governing the amount of perturbation, like the angles, we want to find a local Lipschitz constant that bounds the change in output of the neural network over that range of perturbation values. Because of our generality, we are not restricted to a specific activation function, instead supporting any locally Lipschitz function. Furthermore, our approach can handle general classes of perturbations beyond those addressed in prior works. The perturbation parameter space itself has a low dimension, which we will later show how to leverage for large efficiency gains. Lastly, our method compositionally supports functions containing limited points of non-differentiability, such as those created by Williams. So how are we able to obtain an analysis that is fully general, fully compositional, and highly efficient? We do so by using differentiable programming with a custom forward analysis. The syntax of our augmented differentiable programming language is given as follows, where in addition to the common operations, the branching primitive allows us to encode non-differentiable, yet still Lipschitz continuous functions like rho. However, handling these points of non-differentiability requires special care as their classical Jacobian is undefined. Because of this, our differentiable programming semantics will be defined over the Clarke generalized Jacobian, as this generalized derivative is still mathematically well-defined for both differentiable and non-differentiable functions. Furthermore, the Clarke Jacobian can be used to compute the Lipschitz constant. As the exact Clarke Jacobian is not computable, we will compute an abstract interpretation of it using a forward mode pass. This forward mode pass is highly efficient for small input dimensions, and it will employ a custom fully compositional abstract domain built atop dual numbers. Our abstract domain puts dual numbers to intervals and provides sound transformers for all arithmetic operations and primitive functions. Furthermore, we employ a special join operator to soundly handle the Clarke Jacobian of non-differentiable functions created from branching. Hence, these semantics soundly over-approximate the true Clarke Jacobian. We formally prove the soundness of our abstract semantics, as well as the correctness of the forward mode computation in the paper. We implement our approach in a tool called DJ and analyze several well-known perturbations, specifically haze, contrast variation, and image rotation. We evaluate DJ on a variety of large-scale architectures, including large convolutional networks on both the MNIST and CFAR datasets. For the baseline, we use an existing work to compute the global Lipschitz constant of the network, which we then multiply by the local Lipschitz constant of the perturbation, as this can be thought of as a naive baseline for the problem. Compared to naively computing a global Lipschitz constant, the local Lipschitz constants computed by DJ are several orders of magnitude smaller, hence much more precise. We were able to further improve the precision of DJ by splitting the intervals into finer partitions, as can be seen from the various colored curves. Furthermore, DJ is fast. Even when using the most interval splits on the largest networks, the analysis still takes no more than a few seconds. For those interested, the paper contains a deeper discussion of the following topics, such as the full proofs, as well as additional experimental results. To summarize, forward mode abstract interpretation of the Clarke Jacobian with dual intervals gives us much greater generality and compositionality for tackling new problems, and is still quite fast, since we fast forward the computation of Clarke Jacobians with dual intervals. Thank you.